It's the first time that a dormant black hole has been unequivocally spotted outside of the Milky Way, according to the researchers who conducted the study. Astronomers have just discovered a strange black hole lurking in deep space. But what sets this particular black hole apart from others? Should we have a cause for concern? Let's find out. El-Badri, an astronomer working for the Center for Astrophysics, which is a joint venture between Harvard University and the Smithsonian Institution, has a history of expressing skepticism regarding the discovery of black holes. El-Badri helped demonstrate that the enormous black hole astronomers thought they had found should not exist, just after those astronomers had announced their discovery. Shinar, though, is somewhat of a black hole destroyer himself. He is an astrophysicist at Amsterdam University in the Netherlands, and in March of this year, he was part of a team that demonstrated the possibility that the black hole located closest to Earth might not actually be a black hole at all. All of this alleged destruction is fantastic for journalists looking to make headlines, of course, but in truth, it's just excellent research. As astronomers acquire more data on stars, black holes, and binary systems, they refine their understanding of the cosmos. Today, the two individuals have joined forces, along with a large number of other researchers, not to eradicate an existing black hole claim, but rather to locate a new one. This is quite uncommon and perhaps a little bit peculiar. In a recent study, which was released on July 18th and published in Nature Astronomy, the researchers investigated a binary system located approximately 160,000 light-years away, known as VFTS 243. The researchers spent 6 years scanning the Tarantula Nebula with a very large telescope at the European Southern Observatory, hoping to find stars that might be accompanied by a black hole. They found what they thought they were looking for with VFTS 243, which was a large star that belonged to a group of stars known as the O-type stars, as well as something else. Shinar noted in an email that what they saw in the data was a very large star with 25 solar masses, rotating periodically around something that they could not see. Shinar made the observation that the unidentified star companion had a mass approximately 9 times that of our Sun. The task at hand was to demonstrate that the unidentified object in space could not be anything other than a black hole. According to Shinar, there was a list of potential companion objects that were being considered. It was possible that it was just another regular star, but one nearly 6 times as large as our Sun. Alternatively, it could have been a helium star that had its outer layers stripped away as a result of interactions with another star. There was also the more outlandish possibility that the extra object was actually 2 smaller stars orbiting one another in a binary system. This would have been a very unlikely scenario. Shinar brought the information to El-Badri, who made the observation that the group could not find a logical explanation for the data that did not include a black hole. This was a rather big claim coming from someone who had been heralded as a black hole debunker. He continued by saying, "To the best of our knowledge, there are no other options. It's either a faraway alien that we can't see, or it's a black hole." He said that the fact scientists were able to piece together what came before the birth of the black hole, resulting from the combination of an O-type star and a black hole, makes this phenomenon extremely fascinating. If we had looked at VFTS 243 in the distant past, we would have seen 2 enormous stars circling each other and dancing. In due time, one of these stars would run out of fuel and eventually go supernova. Astronomers are of the opinion that this collapse would, in the normal course of events, result in a tremendous explosion known as a supernova, with a black hole produced as a byproduct. However, the event horizon of the black hole in VFTS 243 seems to have disappeared without producing any explosions. A mystery. This phenomenon is not without its predecessors, according to Shinar. About 10 years ago, theoretical models started suggesting that there should be regions of mass where black hole progenitors do not erupt. According to him, the Paring's almost circular orbit gives what is arguably the first direct evidence of a black hole being formed without the use of an explosion. Another point of interest is that, in the past, astronomers have been able to locate these kinds of black holes by looking at X-ray emissions. However, the black hole in VFTS 243 does not emit X-rays and is not highly active. The group identifies it as a dormant black hole and asserts that it is the first one to be unequivocally detected outside of the galaxy in which we live. These 2 mysteries are essential for understanding the formation of binary black hole systems, and their importance cannot be overstated. Astronomers have been captivated by these partnerships because they emit gravitational waves as they spiral towards each other. However, the process by which they are formed is still a mystery to researchers. Nearly 100 instances of black holes merging have been picked up by gravitational wave detectors in the United States, Italy, and Japan since they came online. According to Shinar, VFTS 243 could provide us with a glimpse into the kind of system that is responsible for the formation of these black hole duplicates, which would make it a very essential component in theoretical models. We have been discussing all of this creation, but let's switch gears and talk about destruction for a moment. The group made a prediction about what would happen to the binary system in the distant future, and here's a spoiler alert: they're doomed. In around 5 million years, the binary system will transform into a system consisting of two black holes due to the ultimate collapse of the enormous star, which will result in the formation of its own individual black hole. This will cause gravitational waves to be emitted as the two bodies continue to orbit each other for what seems like an eternity, until ultimately they will crash into each other. It is estimated that this would take place in a few 100 billion years. At that point in time, though, I have a strong suspicion that not a single atom that constitutes this piece, including you, me, and the birds and the bees, will still be around. The discovery of the dormant black hole in VFTS 243 marks a pivotal moment in astrophysical research, especially as it challenges previous assumptions and opens up new avenues of exploration. This particular black hole is not just another discovery in a crowded field of astronomical objects. It offers a unique opportunity to study black hole formation in ways that were previously thought to be improbable. For one, it is dormant, meaning it is not currently emitting the kinds of energetic signals like X-rays that we typically associate with active black holes. This is particularly intriguing because it suggests that black holes, even those that are not actively feeding or engaging in dramatic processes, can still be detected and studied. VFTS 243's importance extends beyond just the discovery of the dormant black hole itself. The binary system in which it resides, with its nearly circular orbit, provides the first direct evidence of a black hole forming without the usual explosion associated with stellar collapse. In traditional models, when massive stars run out of fuel, they collapse in a supernova explosion, leaving behind a black hole. The idea that a black hole can form without such an explosion challenges fundamental theories about how these objects come into being. It might also provide insights into how black holes behave over time, especially in systems that are not dominated by energetic, explosive processes. Astronomers and astrophysicists alike are captivated by these findings because they could have broad implications for our understanding of the universe. If black holes can form without explosions, it suggests there might be other mechanisms at work that could have been previously overlooked. The fact that VFTS 243 is in such an isolated region, about 160,000 light-years from Earth, also adds to its mystique. It is a reminder that our own Milky Way may not be the only place where complex astrophysical phenomena are occurring. There are countless other galaxies, nebulae, and star systems that could harbor similar mysteries waiting to be uncovered. The binary system containing VFTS 243 also challenges the way astronomers think about stellar evolution. In the case of this particular system, two massive stars seem to be orbiting one another in such a way that one might have already gone through a supernova phase, but without the usual violent explosion. This hints at the possibility that black holes can form in more subtle ways, potentially as a result of interactions between stars within a close binary system. Understanding this could help astronomers refine their models of stellar life cycles, as well as provide more clues about the ways that massive stars evolve under different circumstances. In addition to the direct implications for black hole formation, the discovery also sheds light on the broader issue of how binary star systems evolve. Most binary systems, particularly those that involve massive stars, tend to end in dramatic events, whether through the formation of black holes or through the stars themselves becoming neutron stars or collapsing into white dwarfs. However, the specific circumstances of VFTS 243 suggest that in some rare cases, the stars in such systems may not end in the fiery explosions that we might expect. Instead, they may collapse quietly, leading to the creation of a dormant black hole that is nearly impossible to detect without careful observation. This particular discovery also contributes to a growing body of work on gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by massive objects accelerating through space, and they offer a way for scientists to detect and study black holes, even those that do not emit visible light. The detection of these waves has revolutionized our understanding of the cosmos, offering a new way to study black holes that goes beyond the traditional electromagnetic spectrum. VFTS 243 could be an important piece of the puzzle in this emerging field. If the black hole in this system is indeed dormant, it may not emit X-rays or other forms of light, but its presence could still be detectable through its gravitational influence on its companion star. This could help researchers develop better models for the formation and behavior of binary black hole systems, which in turn could improve our understanding of how gravitational waves are generated. The study of these gravitational waves has already provided a wealth of information about black holes, including details about their mass, spin, and even their merger histories. VFTS 243 could contribute new insights into the types of black holes that form in the absence of explosive events, potentially revealing previously hidden aspects of the universe. The theoretical implications of the discovery are also profound. If black holes can form without the usual explosive process, it could mean that the conditions required for black hole formation are more varied than previously thought. This could open up new questions about the nature of mass, gravity, and spacetime itself. Could there be other, more subtle ways for black holes to form in other regions of space that we have yet to observe? How might these black holes behave differently from those formed in the traditional way? These are questions that could lead to new theories of astrophysics, helping scientists better understand the forces at work in the universe. Furthermore, VFTS 243 represents a unique opportunity to study the long-term behavior of a binary system containing a dormant black hole. The binary system will eventually evolve into a system of two black holes, but this process will take millions of years to unfold. While this may seem like a slow and distant event, it allows researchers to study the interactions between the two stars in real time, observing how their orbits change and how they influence one another. This kind of long-term study is difficult to achieve with many other astrophysical objects, as most events in space unfold over timescales that are far beyond human lifetimes. From a more philosophical standpoint, the discovery of VFTS 243 encourages reflection on the vastness of space and the intricacies of the universe. Every new discovery in astrophysics, whether it is the detection of a black hole or the observation of a distant galaxy, reminds us of how little we truly know about the cosmos. VFTS 243 is just one small part of an enormous, incomprehensible universe, but its discovery underscores the idea that there is always more to learn, and that even in the farthest reaches of space, there are still surprises waiting to be uncovered. In the coming years, as more data is collected and analyzed, astronomers may uncover even more about the nature of VFTS 243 and other similar systems. The fact that a dormant black hole can be detected and studied, even without the usual telltale signs of activity, marks a significant step forward in our ability to explore the universe. It also serves as a reminder that our understanding of space is still very much a work in progress. Each discovery opens up new questions and areas of inquiry, and VFTS 243 is no exception. As we continue to study the stars, black holes, and other phenomena in our universe, it is likely that VFTS 243 will play a key role in shaping our understanding of how these objects form, evolve, and interact. This discovery could help unlock the mysteries of binary black hole systems and gravitational wave production, paving the way for future research and discoveries that will expand our knowledge of the cosmos. And as we peer deeper into space, we will undoubtedly encounter even more enigmatic phenomena, each one offering a new piece of the cosmic puzzle. The discovery of VFTS 243 and its dormant black hole also prompts deeper questions about the role of these cosmic giants in the broader dynamics of galaxies. Black holes are often seen as crucial elements in galaxy formation and evolution. The process by which they form and interact with surrounding matter can significantly affect the galaxies in which they reside. For example, the gravitational pull of a black hole can influence the motion of stars and gas in its vicinity, potentially leading to the creation of new stars or the destruction of existing ones. Understanding the properties of dormant black holes like the one in VFTS 243 could provide crucial insights into these processes, helping astronomers better understand how galaxies evolve over time. Moreover, the fact that VFTS 243 is located in the Tarantula Nebula, a region of active star formation, adds an additional layer of intrigue. The nebula itself is a hotbed for the creation of massive stars, many of which will eventually meet their end as black holes. Studying the interactions between these stars and the black hole in VFTS 243 could offer important clues about how massive stellar remnants affect their environments. It may also help scientists understand why some black holes remain dormant for such extended periods, while others become active and begin to accrete material at much higher rates. Another interesting aspect of the VFTS 243 discovery is its potential to inform the ongoing search for intermediate mass black holes. While stellar mass black holes and supermassive black holes are relatively well understood, intermediate mass black holes, those with masses between 100 and 1,000 times that of the Sun, remain elusive. If the black hole in VFTS 243 is found to be of intermediate mass, it could provide a key piece of the puzzle in understanding how these elusive objects form and evolve. This discovery could ultimately help fill in some of the gaps in the current models of black hole formation and contribute to a more complete picture of the life cycles of black holes in the universe.